other side of that. That never happens, that it just works.
Oh, it just works this time, yeah, great.
Okay, so now let's continue with the adjoint QCD on the Hamiltonian lattice approach, and Benjamin Sogaard will start.
Yeah. So thank you for the opportunity to speak. So Ross and I, we're going to continue talking about adjoint QCD, but now with a slightly different approach of the Hamiltonian lattice instead. And this is based on some work we did with Igor and Silvia Pufa, who's not here today. Silvia also spoke about this model to some extent at the New York meetings. Some of you may have heard some of this talk already, but we're going to extend a little bit, so hopefully there's something new for everybody. Right, so I'm going to start by making a bit of an introduction, which has already been done for me to some extent, by motivating why we're doing this. So Jörg already talked about like theoretical motivations for looking at like kind of these toy models, that like we have some models simple but not too simple. But then we are taking this approach of Hamiltonian lattice models, which is that rather than discrediting both space and time, we have only discrete space, but then continuous time, where we have a Hamiltonian that we evolve with. And then there are like actually a bunch of different people who are trying to solve these kind of problems. So, for example, on classical computers, we have these tensor network algorithms that are very good at solving lattice models for many-body Hamiltonians, and people are also using these for doing gauge theories, and they present new challenges in terms of like understanding gauge invariants and stuff like that. And also people try to do this actually in labs, in experiments, where they're realizing the Swinger model and also try to realize non-abelian gauge theories with cold atoms confined to optical lattices, so you really can realize these models. And then finally, Martin Savage gave a talk to his collaboration not too long ago about how he and his collaborator realized the Swinger model on contemporary quantum computers. And this adjoint model that we're going to talk about is in some sense like the next step up in complexity you could try to simulate on such a quantum device that's available today. Right. So the plan is basically that I'm going to talk about our model and how to figure out what the states are the physical ones, and which one we are supposed to look at to find the spectrum and Carl concept and so on. And then Ross is going to take over and try to translate some of these somewhat abstract things to something you can put on a computer, and then show results for 2 and 3 colors. Right. Great, yeah. So this slide we almost already saw. So it's a two-dimensional gauge theory with an adjoint Mariana and issue in gauge group. And the expectation as already mentioned is that we have this screening of fundamental charges for zero mass, and then it becomes confining for non-zero mass. And then there's an extra nice or interesting feature, maybe surprising, I want to point out, which is that if you tune the mass parameter of your Mariana to be not zero, but some finite mass, in particular this one, which will relate to the number of colors you have, then the spectrum arranges itself in a supersymmetric manner, such that you have some Fermi-Bose pairing, and this was like developed on in light cone quantization. And so this is something we go and try to check on the lattice and see if we can find this supersymmetry, which Ross is going to talk about. Right. So yeah, we're going to try to build this Hamiltonian, and we're going to do this in a sort of two-step process. First, I'm going to talk about just how you put a free Mariana on a Hamiltonian lattice, and then I'm going to add in the gauge degrees of freedom. So if we just take the free mass Mariana, well then the action is the same as before, mod all the gauge structure. And the way we're going to put this on a lattice is by following an idea of Kogan and Susskind, which is that we're going to stagger them. What that means is that we choose some basis for gamma matrices, and in that basis we can think about our spinors as a two-component thing with real entries. And then what we're going to do is we're going to stagger these components on the lattice such that the upper component goes on the even sides, and the lower component goes on the odd side. So we kind of take our fermion and pull apart into two pieces like that. And one could ask oneself, why would you do that? That seems more complicated than just putting both components on one side. But that has to do with the fermion double problem that was solved in Georg's talk by these Wilson fermions. But here, staggering them like this also solve this problem, such that in the spectrum we only find one physical flavor rather than any doublets. Right, so this formulation will give us just what we expect and nothing more. And you can of course translate back and forth between these lattice degrees of freedom, and you get like the dimensionality from the lattice spacing. Right. So what is a Hamiltonian and gives you this free dynamics? Well, it's this one, and one has to consider a lattice of even number of sides, because we did the staggering. So like, if you want an integral number of fermions, then you need to consider an even number of sides. And on each of these real Mariana operators, and they satisfy some Clifford algebra. And then this is the correct Hamiltonian to consider. And one important thing is that we want to put this on a computer eventually. So we have to make the space finite in some sense, and the way we're doing it is by giving it periodic boundary conditions, the fermions. So it has some kinetic term, which is supported on two sides, so it gives some hopping. So something that's a little special for this Mariana model is that the mass term is also supported on two sides. So it almost looks like a kinetic term. But you have to do this, and then there's also this funky sign that has an alternating sign, which can be understood from the fact that gamma naught is antisymmetric. So what coupling down and up component is, down up and down gives different signs. So coupling even and odd and even gives different signs. But like this gives you the right dynamics when you take the continuum limit. And so we can try to upgrade this to SUN gauge theory. And to do that, we start by taking our fermions and trying to arrange them into an adjoint multiplet. So we take NC squared minus 1 copies of them and make them live on every side. And if we took the Hamiltonian from before, then it would now enjoy some global SUN symmetry. But we want to make it local to have our gauge theory. And to do that, we need to add in some gauge degrees of freedom. And because, so in continuum that of course would be given by the gauge potential. But because there's like a finite distance between lattice points, the propagator, the spatial propagator, is not going to be a Lie algebra element, but rather it's going to be a group element that does a finite transformation from one side to the next. And so we can like introduce some local gauge transformations of our fermions, and correspondingly some information of our connections, such that we can make our Lagrangian or Hamiltonian from before gauge invariant. So these terms that were supported on two sides, they are upgraded by putting in a propagator such as invariant, and the same thing for the mass term because they're also supported on two sides. So that would just gauge the fermions by itself, but of course you also need the F mu nu squared term, the kinetic term for the gauge boson. And the way you get that is basically by taking the electric field squared, which is what we call L here. And the reason why I call L is because there's like another quirk from being on a lattice with finite distance, which is that the electric field comes in two flavors, which encode the same information, but there's like an L version that transforms like the side to the left of the link, and then there's an R version that transforms like the side to the right of the link, but they encode the same information and the electric field strength. Right, and because we're in the Hamiltonian formalism, we have another piece of information to supplement our Hamiltonian with, which is the Gauss law, which is the constraint that comes from getting rid of A naught in the Lagrangian formalism. So it looks like any other Gauss law, basically, and because we're in 1 plus 1D, it's particularly simple. It simply just says that, well, the electric field has to go up by amount Q, where Q is like how much charge is on the lattice side when we pass by it, and the Q you can construct with the Clark constants of the group, and then you get this kind of structure. So to actually start looking at this and solving this Hamiltonian, you want to first identify what is the physical subspace of the full Hilbert space where this constraint is satisfied. And the initial on-physical superspace, that's not superspace, Hilbert space is just like the tensor product of whatever space these U's live in and the fermions. So I'll try to describe each of these spaces one at a time. So for the fermionic Hilbert space, we can start by considering the simplest setup, which is like shaving our lattice down to being only two sides. So we have like one full fermion, so this is kind of the minimal thing we can look at. And then we only have these chi's on each side, so that means that we have in total 2 times NC minus 1 Mariana operators that satisfy the standard Clifford algebra. And then to find the representation of these operators, well, then it's just constructing standard gamma matrices in an even dimensional space-time. And then I can immediately write down, well, then the dimension is 2 to the nc squared minus 1. And then, well, maybe surprisingly, depending on how much you've thought about this, then we designed these operators to transform in the adjoint. But that does not mean that the Hilbert space will necessarily, the states in the Hilbert space will transform in that adjoint. And in particular, that is not what happens. In general, what does indeed happen is that under the local transformation, under these two sides, each of them do not transform in the adjoint, but rather in this representation we call R. And then, in addition to, so there are many copies of this, so we kind of need another quantum number which keeps track of which of these copies it is. And this other part of the Hilbert space, which we call the qubit Hilbert space, because it doesn't know about the SUN transformation. It encodes, for example, the fermion parity of the state and other information. But for understanding the physical Hilbert space and solving the Gauss law, it's enough to think about these representations here. So the Young diagram that corresponds to this representation is this triangle here. And you can compute the dimension of it, it's this guy. And so to check that we really did this correctly, well, a check of whether we did this correctly is that we can take two of these, so we square this and multiply by the multiplicity, and then indeed we get back to the original dimension, and so this is like at least one check of the decomposition. So in general, this is like a complicated representation, but in 2 and 3 colors, it's well known, right? Because for SU2, it's just a fundamental representation, half representation, and in SU3, you get the coincidence that it actually is the adjoint representation, and yeah, for higher dimensions, you get like this complicated structure. Right. So, but to extend this to the full lattice, we simply just take copies of this structure. So you get these R representation living already sides, and then in addition, you get this qubit quantum number here, which runs now over this number, but to the nth, because, well, n half, because we multiplied the thing by this many times. So that is the full Hilbert space for the fermions. So for the bosons, well, the operators were these propagators, which are valued in the group. So one way of figuring out what the Hilbert space is, well, just say, well, let's consider a free particle on a group manifold. And then at least if I choose a simple manifold such as U1, then I can easily answer the question, because that would be a free particle on a circle, right? And then the wave functions, the Hilbert space would be spanned by the Fourier modes, and they would have some like energy proportion to n squared. So another way of thinking about this is that this is n is labeling all the E-reps of U1, and all these E-reps are one-dimensional, so like you could think about that being a 1-1 index, and that is really how you generalize this to the non-abelian case. So for SUN, we can then play that game and say we choose an E-rep and a representation of SUN, and then we look at the collection of all its matrix elements, so it has a left and right index, and they're gonna be the wave functions in this Hilbert space. And if you had the free Hamiltonian, then you would just get the second Casimir as energy. So you can also write this, of course, in like some Ket form where you choose the representation, and then you have two indices in your matrix element. And to generalize to the full lattice, you just take copies all along. Right. So now we can splice it together to get the gauge invariant states. And it turns out, at least intuitively, it's not so hard, because or maybe, let me just reiterate what we have. On the sides, we have these representations R, and on the all links, we can choose a representation, which like, we can, yeah.
Can you just explain how you knew this R for the fermions?
Yeah, well, so initially we just found out by playing around, but we have a proof, like in terms of characters, that you can, if you stare at how you look at the projection, well, so technically what we do is we like calculate some branching, and you can find out this multiplicity by so this spinner E-rep. I'm sorry, this is the wrong direction. It's still the wrong direction. Good. So the way we constructed these were by doing like gamma matrices in some bigger orthogonal group, and then by figuring out what projection into the local SUN from the operators, then you can ask, well, how does this spinner E-rep then branch? And that's how you find it in general. Yeah, good question. Right, but nonetheless, that's what lives on site, and then we can choose representations on the link. So to solve the Gauss law, well, then we have to say that the electric field to the right of the site has to be equal to the charge on site plus the electric field to the left of the site. But of course, we need to phrase this in a group theoretical manner. So that means that for this to be a valid representation to live here, it must live in the tensor product of this guy, R1 with R, and so on. So this one, for that to be valid, it has to live in the tensor product of R2 and R. So technically, you can write down what these states are by contracting with a bunch of Clebsch-Gordon coefficients that are going to soak up all the M indices. And what you're left with is really only these labels on the links, all the representations that you chose. So that gives us like what is the space of states that we can think about that are actually gauge invariant. Well, they are labeled by all these representations, subject to the constraint that I just told you. And then in addition to this, we have these qubit degrees of freedom, which encodes some additional information that doesn't concern the SUN transformation. Great, right. So now we have constructed this space of states, but actually something more we can say about it, because this representation R that lives on site, it has anality NC halves when NC is even and 0 when NC is odd. So that means that if we think about these valid states, then for even NC, then the anality is going to alternate by this amount, because like 2 times this is NC, which goes back to itself. And for odd NC, it's constant. So that means that if we decide to only think about or focus on the even sides for a moment, then we can classify all these states by what anality lives on the even sides, which breaks this physical subspace into some super selection sectors, NC of them, and this is really what is known as universes, sometimes in literature. And to kind of exemplify this, we can just do some explicit example with some simple groups. So here I want to construct an anality 0 state in SU2. So I go to an even link and then I put some anality 0 state representation there. So for example, spin 1 representation. And then to go to the next link, I have to add the spin half representation. So that means I can either go up to 3 halves or down to 1 half. Here I chose 3 halves, and then you just go on like that. And if this is a whole chain, then it's like periodic, you go back. And as promised, the anality alternates because it's even NC, so it's 0, 1, 0, 1, or integer, half integer, if in the SU2 language. So that's that case. So if we upgrade to SU3, then things become more complicated. There the on-site representation is the 8th adjoint. So we can again try to construct a state with 0 anality. So we can start by putting a single sample on this even side. And so we have to tensor the singlet with 8, so we only get the 8. But then when we take 8 with 8, then we get a bunch of things, for example 10. And so we can continue like that. But then there's like a further complication, because when I get here, then I have the 8 with the 8 again. And now, this tensor product actually has an outer multiplicity for 8, there are 2 8s in it. So to enumerate all my states, I really have to tell you not only that I'm putting the 8 there, but also which of these 2 8s I'm choosing, else I wouldn't get all the states in the Hilbert space. Right, so this is a space of states. And the last thing I want to tell you before I hand over to Ross is why this particular realization of adjoint QCD is natural from a symmetry point of view. Because in this paper they figured out what are the symmetries of the continuum theory on a circle, and has kind of this structure where you have a center symmetry, charge conjugation, fermion parity, and a chiral rotation, which basically flips the up and low component of your spinner. So this is not exactly true, because the chiral rotation is only at 0 mass, and the charge conjugation only acts non-trivial for NC larger than 2, because SU2 is pseudo-real. But the point is that we have like explicit analogs of all these symmetries in this Hamiltonian lattice model. And the 2 most interesting factors in this is the one-form symmetry and the chiral rotation. So this one-form symmetry, it's a one-form symmetry, so that means in 2 dimensions it's supposed to be a topological point operator. So no matter where inserted, it should do the same. And it's supposed to tell me what universe I'm in, so we measure what anality the universe has. So naively you would think that it would just be like this piece here that measures the anality. But I just told you that in even NC, you're going to have an alternating anality. So you need to put in this extra factor here such that you actually measure the same anality of the universe everywhere, and that makes it topological. You can just insert it anywhere. The other thing that's realized in an interesting way is this chiral symmetry, because we stagger the fermion, so the up and down component are on adjacent sides. So if I want to switch them, then the way I realize that is by actually doing lattice translation by one side, which effectively implements chiral rotation. And of course, this is like an analog in the sense now it won't any longer square to 1 like the true chiral symmetry does. Instead, you have to like take it to the nth power, so go all the way around the chain. So this is related to these eminent symmetries, but still, like this is a symmetry of a lattice Hamiltonian, but only at m equals 0, because if you remember, the Hamiltonian had this alternating sign on the mass term. So if we have a non-zero mass, then it's going to break this symmetry. Right. So as said, we also have explicit realizations of both charge conjugation and fermion parity, but they work pretty much as you would. Yeah.
I'm curious. I'm not sure I followed. So the chiral symmetry is a translation by a. Is it really a translation by a side, or is it a translation by a half side?
By a side, right? Because well, so depending on what the language is.
Staggered fermions.
Yeah.
So actually, you have fermions living on sites and dual sites. So
yeah, you can say, and then in that language it would be a half side, right?
Good. So then it squares to a single translation.
Yeah, correct.
Which is a symmetry, so it's okay.
Yeah, so I get back to symmetry, yeah. And that's why there's this eminent symmetry story that if you take a continuum limit, then it's going to be a mix between the real chiral rotation and a translation.
So the reason I perked up is I wouldn't. You shouldn't have to go all the way around to get it.
No, yeah. So in that sense, it's mixed, but there's more good news other than it's like a symmetry of the massless Hamiltonian, because, well, as you also show in this paper, you find that there's a mixed anomaly between the chiral rotation and the other factors. And if we take or explicit realizations of these operators on the lattice, no continuum, then they have the same anomalies. So we compute the algebra and we get the same projective phases as in the continuum, and like that's like further justification that this is the right thing, the right chiral symmetry to think about.
Can I ask one more point?
Yeah, of course.
I think that's really beautiful, but I'm also wondering, what about the non-invertible symmetries? Are they visible here, or?
Well, so Russ going to talk about like that. It doesn't seem well. These 4 Fermi terms don't see like it.
Not the 4 Fermi terms, the non-invertible symmetries.
Yeah, but like the answer is like we don't really know what the status is. So what I mean is like we only have some sort of indirect evidence by the fact that it seems.
It's an open question.
Yeah.
It may depend on NC, right? Maybe for different NCs, the answer is different.
It's possible.
Yeah. Yeah, and one last thing that's nice about this lattice realization is that in even NC you find this anomalous relation here where when you act with the chiral rotation, then you go to another universe. But that's very easy to understand in this realization, because for even NC, then you have this alternating anality. So if you do a translation by one side, then you're going to change the anality, and so you're going to go to another universe. So it's like very explicit in that sense. Right, but now I'm going to hand you over to Ross, who's going to talk about how we can do this on a computer.
Great. Excellent beginning. So, right, as Benjamin was saying, we've dreamed a dream here with a theory that gives a lattice realization of all these theories and their anomaly structure, and my job for the remainder of this talk will be to make that dream come true, at least for SU-NC theories. So let's talk about what the remaining ingredients are to put this on a computer and then see some results thereof. Okay, so really what we need here is an explicit representation of all these Majorana operators living on each site and with their adjoint indices, which obey the correct algebra here. And so what we want to do is construct explicit realizations of these operators that act on the Hilbert space that Benjamin described. So the Hilbert space that has this representation R living on each site and representations on links and so forth. And so what we're going to do is attempt to build these chi's in that language. So back to the story of the representation living on each site. So with this representation R, Benjamin was telling you it's the fundamental representation for, it's the fundamental representation for SU2. For SU3, by coincidence, it's the adjoint. For higher NC, it's something else, like the 64 for SU4. It's some kind of funky representation. Now, if we want to write a operator with an adjoint index as something that acts on the sites. The gauge invariant way to do that is to have an invariant tensor that carries this adjoint index and then acts as a matrix on that representation living on the site. So it carries two R indices. And so we can just explicitly look and see what those invariant tensors look like. So for SU2, we were looking for an invariant tensor with an adjoint index and two fundamental indices. These are the familiar Pauli matrices, and so that's what appears in the story for SU2. For SU3, we're looking for three adjoint indices. Well, those tensors are the F and D symbols. We have, in particular, two of them. In fact, one can show in general that for arbitrary NC, there are NC minus 1 invariants with these indices. In fact, even more generally for any group, it's the rank of the group counts the number of these tensors. And so we have that many ingredients to play with when we write down our Majorana operators. So let's refer to these invariants by C with index J labeling how many there are, 1 through NC minus 1. And so once we pick a basis for these invariants, and I'll come back to the choice of basis, but once we pick a basis for these invariants, we can write our operators as sums over those invariants acting on the R representation living on the sites. And then there's another factor that acts on these auxiliary qubits that live on pairs of sites that Benjamin was describing as the multiplicity of the R representation living in each pair of sites. So these factors are really just Pauli matrices, and these are really just qubits. And so acting with these operators is really just like working on a spin chain Hamiltonian. So I'm not going to go into too much detail on these. Suffice it to say they're very explicit and very computable. The more interesting piece is these CJs. And in particular, we need to choose them in a way such that these chi's will satisfy the algebra they need to satisfy. So let me talk briefly about how we can do that. Good. So if we want to have the chi's on the same site to satisfy this anti-commutator, one can work through what that means in terms of the CJs and the chi's written on the previous slide. And one can show that the condition is that some sum of anti-commutators of these C's gives you this delta symbol on the right-hand side. That's, if you expand this out in components, that's a ton of equations. But really what we can do here is expand this equation into invariants of the adjoint times R times R. Those are the indices that are appearing here. I've suppressed the R indices, but each of these C's carries two R indices as a matrix over the representation R. And so once we decompose into those representations, there's actually many fewer independent equations contained here. And in fact, we have exactly the right number to solve for a choice of basis for the CJs. So some rotation of the CJs that makes this true. So we can do that very explicitly for any number of colors, find these CJs, and then that is going to fix the definition of these Majorana operators. And so now we have a very explicit Hamiltonian. If you interpret these, the chi's appearing in the kinetic and the mass terms as these sums of some Pauli matrices times these invariant tensors, it's a very explicit Hamiltonian, and all we want to do now is compute its matrix elements in order to put it on a computer. So it's an explicit problem, but it's a hard one. Let me describe what it will look like. So remember our this Hilbert space. There's a part that has these qubits. This again is explicit computable, not that interesting. And then there's this H prime piece that carries this representation R on each site. And so we're going to focus on that piece. So Benjamin was describing for you how we build our states in terms of contractions of many Clebsch-Gordan symbols. So let me just clarify the diagrams I'll use to represent these contractions. A Clebsch-Gordan symbol, right, takes two representations, fuses them in their tensor product, and then picks a representation that comes out. And so we'll draw these symbols like this. Note especially that there is an index, a sort of hidden index living on each of these nodes, counting that multiplicity. If the representation appears more than once in the tensor product, then one has to keep track of which one of those comes out. I'm going to suppress those indices here, but just know that they are floating around. It just makes it a lot messier, but they're there and they're important. We sum over them in several places here that I've suppressed. In any case, we have these sites that are built from these contractions of Clebsch-Gordan symbols, where in particular on each site a representation R comes in and fuses with the previous link representation to build the next one. So what we want to do is take a state like this and then act on it with this term appearing in either the kinetic or the mass terms. Both of these terms are going to have this chi n plus 1 contracted with this link object. And so when we expand chi and chi n plus 1 in terms of the invariance C, we are going to have this contraction of two of these C invariants where by these dashed lines, I mean representation R. It has two of these indices. And the dotted line is the adjoint index, which is contracted. Good. So this is the object we need to act on this state with. And so let's see what happens. So let me actually clarify. So if we take this object and act on, say, these two links, these two sites around the link n, and then sandwich that into another state, the matrix element we'll end up with, right, is this the same link from the original state. We have this contraction of the two C invariants, then everything else is relatively simple. This is the piece that matters for us to compute the matrix element. And so we need to compute this relatively messy contraction of Klebsch symbols, right? The two C's and then the 4 that came from the state and the other state we're looking at the matrix element for. So our job now, if we want to actually compute a Hamiltonian that we can actually diagonalize, is to compute these group theory numbers. Typically, computing group theory numbers is not the hardest part, and for SU2 and SU3 that's very true, but this scales quite badly, as I'll describe in a moment. And so one important trick we can do to simplify this problem is instead of taking this full sort of loopy diagram of the Klebsches, one can use the fact that if you look at this loop here, right, so we've got 3 links and three nodes here, and out comes 3 representations. Well, the only invariant symbols on 3 representations are the Klebsch symbols, and so we can decompose that loop into nodes, which would be this node here. And the factors that come out from this actually sort of look like the mirror image, and they are what are called the Wigner 6J symbols. So these special contractions of 4 Klebsch-Gordon symbols. If you've seen them in the SU2 context, sometimes they're written in terms of this sort of tableau of 6 representations. In any case, it is a huge improvement to use this trick to simplify the symbol, in particular for SU3 when we're computing these 6J symbols. If you use this version for a particular set of parameters, it would take about 100 seconds. Using this decomposition, you can improve it by a factor of 10. Now, while we could have waited 100 seconds for SU3, that's no sweat. For SU4, it becomes over 1 terabyte of RAM, dozens of CPU hours. This kind of trick is a major improvement. On that note, a major question for us is how to more efficiently compute 6J symbols. That's one of the leading issues in going to larger NC. Right now we have to explicitly compute the Klebsch invariants and then contract them, and this seems maybe not ideal, but it seems that there are some open questions in terms of how to efficiently compute these 6Js. So it's a topic of interest if anyone wants to discuss. In any case, this is how we will get our matrix elements. And so now we're in a place where we can compute these giant matrices of sums of products of 6J symbols, and then put them on a computer, find their eigenvalues, and look at the spectra of these theories. So let's go ahead and do that now. If there are any questions, I'll take them before we go to results. Okay, results. Good. So just to clarify what we're diagonalizing here, and to give you a sense of how badly this scales, so we're going to truncate the Hilbert space by including only enough representations to see the lowest few levels in the pure gauge theory. So in a particular limit where the adjoint fermion decouples, we would want to see levels that are just the Casimirs of representations of SUN. We can actually explicitly figure out what those states look like on our basis, and so we keep exactly the representations needed to have those states in the basis. So for SU2, even if we want to go to 12 sites, we want to have the lowest 3 levels, it's only like 50,000. That's fine, that's great. For SU3, even for just 6 sites, if we want to have the same truncation parameter, you're diagonalizing a matrix of rank 500,000. That gets thorny. Here comes SU4. It scales really, really badly. Yeah, Alexi.
How fast does it converge with R?
That's a great question. It's something I'm still investigating. So for
SU2, let's say.
For SU2, it converges very well. For SU2, you really can't see a difference between 2 and 3, for instance.
Going from 2 to 3 changes the answer by what?
A percent or less.
Percent.
For the low-lying stuff we're interested in a particular regime. You can imagine if you take the lattice spacing very small, for instance, then the term in the Hamiltonian that penalizes large representations becomes small, and then it would matter. But in a in a typical regime where, I'll show you in some plots where it would matter.
To be near the continuum level?
Yes, but not too close. I'll clarify in a second when I show you some plots. Yeah. Good. Yeah. So right. So yeah, for SU2 and for SU3, yeah, the convergence is quite fast in this parameter. For SU4, there's some evidence that it might be a little bit slower. But we're still working through the SU4 case. But suffice it to say, yeah, the scaling is quite thorny, and so that's another impediment to going to larger numbers of colors. And so for the results, I'll mainly show you SU2 and SU3. Good. So to clarify what I meant by that truncation parameter first, so let me show you now some plots of spectra. So this is going to be a particular limit, sort of just different from everything else I'll show you, where we take the mass of the fermion very large, so that it decouples, and then we take it also equal to the inverse lattice spacing. The reason for this is that it simplifies a lot in that particular regime, because the mass term and the kinetic term can have some cancellations. And so that's where one can actually explicitly solve this and show that precisely there. So this is at a lattice spacing and coupling units of 1/25. So where m equals 25, we should see exactly the pure gauge theory eigenvalues. And indeed we do. So these lines in the plot show you SU2 Casimir values, and we see the energies from our lattice model lining up perfectly with those. And so this is the truncation parameter 3, where for each universe, equals 1 universes, in each universe we have the lowest 3 levels in that limit. Similarly for SU3, one can do the same thing. I've shown you p equals 0, p equals 1, p equals 2 would be degenerate, and we find this tower of values. SU4, similar story, although you can see it's struggling a bit more to converge anywhere near that value. And again, this is the case where it's even very hard just to compute the matrix to diagonalize here, let alone to diagonalize it. So this is all I'll show you for SU4. It's ongoing work, but the convergence does seem to slow down a bit. Okay, so on to some more physical plots involving the adjoint fermion. So here's a plot showing you the eigenvalues for the SU2 theory as a function of the circle length. And so a few features I'll note. One, so we have this bosonic vacuum, which I've subtracted out from everything. And so we're seeing the energy differences from the vacuum. This first state is this lowest fermion. We know its mass from DLCQ or as well as other studies. And we can see that, so I'll show you on the next slide, but its mass is consistent with the DLCQ. We can also get its mass from a strong coupling expansion, which is this green line. All these are consistent with each other and with previous results. To answer Alexi's question now, finally, so if we go to the very small circle limit, one can see, so I'm just to focus on one point here, right? Where this blue curve comes down and meets this black line, which is a theoretical expectation in the small circle limit, and then starts to curl up a little bit. That's what I mean by too small. That's when you're taking the lattice spacing so small that one needs more representations in this truncation scheme to accurately represent the state here. So this little curve here is the only effect of the truncation of states for this SU2 theory. Yeah?
I'm not quite sure I'm following. So don't you want to fix the physical size? Excuse me, you want to fix the physical size and take the lattice spacing to be small. I mean, obviously, if you take a fixed number of lattice sites and just make the lattice spacing small, then you're exploring some tiny and physically tiny circle. That's not
absolutely, yeah. And so, indeed, and so what we would like to do is fix the size of this length, and then take n very large as we take a very small.
Yes.
The problem here is that n is fixed at 12 in this case, and so
there's not a manifest continuum extrapolation.
Exactly. So one hopes sort of everywhere except the very far left of this plot that you're getting pretty close to a continuum extrapolation.
But the fact that your results appear to be consistent with DLCQ is a hint that you're not too far from the continuum. Exactly. That's how you're interpreting it.
Exactly. And if I showed you several versions of this plot at n equals 8, 10, 12 sites, it changes almost not at all. It changes very slowly, showing that it's converging well.
So this is in the zero?
Yes, I'm sorry, I should have said. This is all for zero fermion mass. I'll show you some results in a bit with non-zero mass.
Yes, one lesson from this is that the small circle limit, which is analytically tractable, from that you would never get the
That's right, that's right.
masses somehow.
Yeah, so one can look at the analytic expectation in the small circle limit where we have, it becomes a tower of harmonic oscillator levels, and we see the lattice reproducing this. One can also do a lattice strong coupling expansion where the lattice spacing is very large, or equivalently the coupling is large in spacing units, and one can figure out what happens there, and one can do a bit better to extrapolate that to the continuum. But what we really care about is sort of a middle region where A is, the lattice spacing is not too large, not too small, and we're in a regime where we can converge towards the continuum limit.
So can you explain this? Different colors, different levels? Is this something what you expect?
Oh, sorry. My color blindness often makes me forget to explain the colors. The blue is bosons, the red is fermions. So this is a bosonic vacuum. This is the lowest state, which is a fermion, which is known from DLCQ to be the lowest one. The next one is a boson, which is known to be the next state, and I'll show you actually on the next slide. It's
The several blue lines converge into one, and again, that's...
Yeah, so one can understand this in a lattice strong coupling expansion. As Igor was saying, it probably doesn't contain many lessons for, they split apart when we come closer to a regime where we're under better control. So yeah, one can understand why they group together, but it's probably not telling you much about the continuum theory. Good. So let me show the consistency now with the DLCQ eigenvalues. So if we use plots like the one I just showed you at different numbers of sites to figure out the mass of this lowest red line, which is the lowest fermion, and the lowest blue line for the boson, one can look at these values for successive numbers of lattice sites and see how they converge as we take the number of sites large towards values about 1.35 and roughly 1.8, which are consistent with the values we know from DLCQ. So in this work we showed that in these units the lowest fermion has mass 1.35 and the lowest boson has mass 1.85. So everything is beautifully matching up here for the SU2 theory. So this is encouraging for our lattice Hamiltonian. I'll show you now an analogous thing for SU3. For SU3, as I was showing you, we can't really go to many different numbers of lattice sites. The number of states grows way too fast. But I'll show you the spectrum for 6 sites. Here again, we have a bosonic vacuum, this time doubly degenerate, though it's not shown in the plot. But then, importantly, the lowest fermion here is getting pretty close to this red transparent line, which is the expectation from DLCQ for the mass of the lowest fermion in the SU3 theory. And likewise, this lowest blue line seems to be matching up with this, again, the DLCQ expectation.
But why do you say it's matching? It's going down.
Well, good. So this is why I can't show you a plot analogous to the one before. So one hopes that there's a small circle region, which is it's a different limit. There's this large circle region where, I should say, a lattice strong coupling region where A is very large, this fixed number of sites on this plot. And it's sort of in the middle where we would hope to see, so as we grow the number of lattice sites, this sort of plateau region will grow and grow and grow, and that's what we should be extrapolating to see the continuum limit. So it's a bit subtle to figure out what we should take from these plots, given that they contain a number of different regimes.
Here the large L is achieved by just making lattice spacing large, right?
Exactly. This is all a fixed number of
Start
sites.
from continuum limit.
Yeah, that's an important clarification. Yeah, it's a fixed number of sites, so large L is really lattice strong coupling. And so it's this, as the number of sites increases, the size of this region will grow and grow and grow, such that you would eventually call that your large L. Okay, and so a neat point that we learned from DLCQ and that we're confirming here is that the 1 over NC corrections seem to be quite small. So one would expect you might have this sort of leading scaling with the tough coupling for the mass, and then as you get down to SU2 and SU3, you might expect relatively large order 1 corrections to it. In fact, it's not the case. These formulas are very close to being exact, and our lattice is not precise enough yet to even be able to probe the corrections. With DLCQ, we probed the corrections and saw that they're several orders of magnitude smaller than these leading terms. And it remains an open question sort of why a deep level that is. That's consistent with everything we're seeing. So, yeah.
So you also get good expectations for the ground state energy also with DLCQ? Because I thought usually the vacuum is very subtle in DLCQ.
The vacuum is very subtle, yeah, and so it's these gaps that we can explain with DLCQ. I'll show you in a minute something we can't do with DLCQ, we can do here, and which is also consistent with this NC behavior.
And this statement about the small NC, it's that the coefficients in front somehow of the 1 over n corrections are also very small.
Yeah, exactly. Yeah, such that even at NC equals 2 or 3, the overall effect is small. That's right. Good. Okay, for the sake of time, I'll just quickly flash a few plots showing the supersymmetry that Benjamin was advertising. So the supersymmetric mass for SU2 is 1 over square root pi, which numerically is about 0.56. I'm showing you here as we get to 0.5, the red and the blue points are getting pretty close. And I'm showing you this because at the exact supersymmetric value, you almost can't even tell that they're 2 points, but there are. This is almost exactly degenerate boson and fermion states, and likewise for several levels higher. And so we do see evidence of that supersymmetry on the lattice. Likewise for SU3. Supersymmetric mass for SU3 up by a factor of √3/2. Similarly, blue and red points are nearly merging for our lattice data. So I'm happy to talk more about that later, but let me move on to the chiral condensate. So this is an example where we're looking at the ground state on this lattice, and then figuring out the expectation of, say, the mass operator in the Hamiltonian, which is related to this trace of psi bar psi in the continuum, and normalizing it by the Chuff coupling and by the number of components of this adjoint fermion. The same normalization that Georg was just showing us, up to a factor of 2 in the trace. And what we see is, okay, for SU2, this normalized chiral condensate comes down to about minus 0.087. If we take, and this may be a better place to see how the limit is done, for any finite n, we're sort of peeling off at small a, but if we take the large n limit, we see that we're moving towards this line. So we can imagine we're first taking a large n limit to get rid of these effects, and then taking the a to 0 limit to get the continuum value. Now, that's the SU2 result. I can show you the same thing for SU3, and we find that's numerically very close, and the small difference is probably as much due to lattice precision as anything else. And so we see that it's nearly the same value when scaled this way. So this is consistent with these small 1 over nc squared corrections, where you might have expected this value again to be some large n value plus small corrections, and here we see that the corrections are indeed quite small. Yeah, Alexei.
You said it verbally, but I didn't quite follow. How are you getting the infinite volume limit for this?
It's good. So if so, for any finite n, finite a, I can get you a VEV in the lattice, right?
So it should be 0, right? In the massless, well, chiral symmetry should not be spontaneously broken. And
It's a Z2 chiral symmetry.
But if you're in a finite spatial volume, you are in quantum mechanics effectively, so it should not be spontaneously broken. In quantum, you can dimensionally reduce to quantum mechanics physically. So
It's a Z2, it's not a U1.
it doesn't matter. In quantum mechanics, Z2 symmetries cannot break spontaneously. At long wavelengths, you're in quantum mechanics. So that's why I don't understand.
We should discuss further.
Let's discuss more later.
I can tell you that, so this is the value for the p equals 0 universe, and the p equals 1, one gets the opposite sign value. That's probably related, but yeah, let's discuss more.
For Schwinger model, this was measured many years ago in exactly the same way.
Precisely, the Schwinger model is quite subtle for reasons that I'm not sure apply here. Let's talk more.
Let's talk. Yeah, great. Okay. But yeah, indeed, modulo those caveats. It seems to be consistent with this near exact Chuff scaling. Good. So let me quickly wrap up. So the idea here is that this Hamiltonian lattice is giving us a really powerful tool that we can, in addition to already existing tools, that we can use to study the theory of adjoint QCD2. And so, in particular, this Hamiltonian lattice formulation has analogs of all the symmetries we expect for the continuum theory, and evidence from the Schwinger model suggests that that's a really key aspect of how it is able to converge relatively well to the continuum theory. And so we can give an explicit implementation of the model actually for any SUNC gauge group, and so far our results are consistent with other work and encouraging in the new directions they can explore. Lots of things on the wish list for this project. One is using the technology of tensor networks in DMRG to get better convergence and better numerics and be able to explore new things. On a similar vein, tensor networks allow us to study the real-time dynamics of these theories, which is a huge area of interest for a number of people. I think this would be really neat to explore for this particular theory. And finally, an ongoing open question is to investigate the four fermion deformations, both to explicitly include them in our lattice Hamiltonian, to understand how, if at all, they appear due to our lattice regularization, and indeed to understand the fate of the non-invertible symmetry on the lattice. That's an interesting open question for us as well. We don't have anything to say on it yet, but hopefully in the future. And I'll wrap up there. Thank you.
Thank you very much. Questions? Further questions?
Just a comment. I think you can see psi bar psi precisely because universes don't mix, right? There are two.
For NC equals 2, I agree, there's no problem with my comment. But for NC equals 3, I don't.
Oh, good. NC equals 3, I should have said. I'm sorry. For NC equals 3, there are two vacua. I've made the mass like 1 times 10 to the minus 6 to split these two vacua, and this is going to be the lower one.
In principle, they would, in the massless limit, they would just mix and you get contributions from both and you get 0 that way.
I agree, yeah. There's an order of limits question here.
It's order of limits that I'm worried about, yes.
Yeah, and indeed. So I've explicitly made the mass very small but non-zero so that we can split these two vacua and see this value.
We can talk more about that. I think there's some interesting things here. I actually had a question. So is it very difficult to measure the expectation value of, let's say, math operators squared?
It's not difficult. One could do this. We should talk about that if that's interesting. Yeah.
Maybe another question. So,
I think he was first, but then.
Okay, so just concerning this study of the lattice spacing, what are, in units of the lattice spacing, what are the this lowest mass gap? What is it?
So for instance here, or better yet, SU2. So here this is, oh sorry, in units of lattice spacing. Well, I'll tell you that this gap in units of the gauge coupling is this 1.35 value. In units of the lattice spacing, one would have to.
Yes, it's 0. It's 0 in the end, in the limit when I mean, it's much smaller than 1 over A.
Right.
I mean, the mass gap in this theory is set by G. Young-Mills in the limit of. It's insensitive to 1 over A, right? Like that's what.
Yeah. We should have a value that does not depend on.
But I mean, at some point you get corrections, and that's why I want to compare those corrections with value.
Ross can probably plug.
Yeah, we can.
Okay.
Yeah, I don't have this offhand, but we can generate this data for sure and compare it with your work.
It's a test of how close you are to the continuum.
Yes. Basically, because you have only a small number of lattice points. I know, but it's always a question in what unit.
Yeah, we can definitely make that data and compare. It'd be interesting.
yes. So when giving the mass to the supersymmetric point, I thought the expectation was that there is a ghost spin of air. There's a massless state.
Indeed, yeah, that's a great question. Thank you. So what I'm showing you here, for instance, for let's take SU3. No, let's take SU2. That's a little bit simpler. So for SU2, we have in the P equals 0 universe, that's what I'm showing you here, there's a single bosonic vacuum. Above that, there's Bose-Fermi degeneracy at every level. In the P equals 1 universe, there's a Goldstino, and we actually do see a degenerate fermionic vacuum there, or nearly degenerate. Yeah.
Any other questions? If not, let's thank the double header again.